Modern AI, everything from ChatGPT to self-driving cars, runs on a single algorithm called backpropagation. Here's how it works. It propagates error signals backward through the entire network, layer by layer. But here's the catch. During that backward pass, every single neuron in the network must freeze. Nothing else can happen. It requires a global controller, something that orchestrates the entire process, but no biological brain has anything like that. Real neurons don't take turns. They fire simultaneously, continuously, all at once. There are no frozen phases. Biology uses no central coordinator, no master neuron telling others what to do. So here's the million-dollar question. How does the brain actually learn? We need a biologically plausible alternative, something that works the way real brains do. What if I told you the brain is a prediction machine? That's the core insight of predictive coding. In this framework, higher layers in the brain constantly send top-down predictions to the layers below them. And what comes back? Not everything, just the prediction errors, only what the brain didn't expect. Predictive coding is fundamentally an energy-based model. The total energy of the system equals the sum of all square prediction errors across every layer. And learning is simply rolling downhill on this energy surface, minimizing that total error. Each neuron has a simple job: align with the predictions coming from above and better predict what's happening below. When these opposing forces perfectly cancel each other out, that's equilibrium, that's understanding. Let's break down the mathematics. The entire algorithm rests on prediction errors. Step 1, generate a prediction. You take your weights W, multiply by your beliefs mu, and that's your prediction. Step 2, calculate the mismatch. The error epsilon equals your actual input minus that prediction. Step 3, update to minimize that error. The change in beliefs is simply the negative of the error. And this happens continuously. The network doesn't stop. It flows down the error gradient in real time. Now, here's where it gets really interesting. Every layer in the brain needs two distinct types of cells. First, representational neurons. We call them mu. These encode the brain's current best guess about reality. Second, error neurons, epsilon. These encode exactly how far off that guess was from the actual input. And this is where predictive coding gets its name, from these dedicated error computing neurons. Error neurons receive excitatory input from their local neighborhood, what's actually happening. And they receive inhibitory input from the predictions coming down from above, what was expected. The remarkable thing, this matches cortical anatomy almost perfectly. The biology was there all along. So the network reaches equilibrium, predictions match reality. Now the real magic happens, learning begins. The update rule is beautifully simple. The change in weights is proportional to the error times the activity. How much should a synapse change? It's determined entirely by local information, nothing global needed. This is a Hebbian rule, one of the oldest ideas in neuroscience. Neurons that fire together, wire together. It's that simple and it's that powerful. This is exactly the local plasticity that neuroscientists have been observing in real brains for decades. Now, let's zoom out to the biggest picture possible, the free energy principle. Every living system, from bacteria to human brains, exists in a narrow band of possible states. To survive, organisms must minimize surprise. They need to stay within states that are compatible with life. Free energy is an upper bound on surprise, a mathematical ceiling that's actually computable. Here's the key. minimize free energy, and you minimize surprise without ever having to compute surprise directly. And here's the beautiful connection. Gradient descent on free energy is predictive coding. They're the same thing. Every single prediction error that gets reduced means lower free energy. The math unifies everything. Let's put them side by side. On the left, backpropagation. The neurons must freeze during the backward pass. Information flows in strict sequential phases, forward, then backward. No overlap allowed. On the right, predictive coding. All neurons update simultaneously all the time. Everything is computed using purely local information, no global error signals needed anywhere. And here's the kicker. At equilibrium, predictive coding's gradients converge to exactly the same values as backprops. This is distributed intelligence at its finest. But predictive coding goes further. It's more robust to noise, handles uncertainty naturally, and avoids catastrophic forgetting. So where does this lead? Predictive coding processes information in parallel, all at once. Just like biological neural circuits have been doing for millions of years. It's inherently energy efficient. Only the errors need to propagate, not the full signal. And it's both discriminative and generative. It can perceive the world and imagine new possibilities. This is where neuroscience meets machine learning, a unified theory of intelligence. When all prediction errors vanish, the model doesn't just compute, it understands. The future of AI isn't about building bigger models. It's about building smarter architectures, architectures inspired by the most powerful computer ever created, the human brain.